Great. So I think we'll have our very last talk, actually the end of the module 2 before we have our demo day next week. So we're very glad to have Greg here to talk about OK Turtles using blockchain for security purposes as well as identity. So maybe Greg, you want to do an introduction of yourself and give us maybe explanation on what does OK Turtle come from? Anything related to OK Google?
OK Google?
Yeah, I'll just do it.
Okay. Hi, my name is Greg Slepak. Thank you guys for having me here today. Thank you for coming as well. Hope you're all well rested. If not, I hope after this talk you take a nap or something. So, I am interested in the field of information security. And you can think of InfoSec as a level above cryptography, with maybe some other fields like systems analysis mixed in. It's not as mathematically oriented as cryptography. It's basically cryptography applied, as well as other fields applied, like OPSEC, operational security, etc. All of these fields are related to one another. Information security is about securing your data. And oftentimes it touches on the topic of privacy as well. And this is something I encourage everybody here to engage me on today, is this difference between privacy and security. And if I do a good job today, I will discuss what those differences are and illustrate them much more starkly and clearly. And the topic for today has a lot to do with DNS. And DNS is a great way to have that conversation about what the difference between privacy and security is, and why you want one, sometimes want the other, some people want both. And what does this have to do, what does DNS have to do with blockchains? So we'll be talking about that. Can somebody get that door, just like close it? Thank you. So, my interest in information security started with a simple desire to secure email. It's a still unsolved problem today. The closest that we've come to solving that problem is GPG, and for 99% of the world, GPG is not a solution. I started by solving it simply encrypting email on a laptop, so that if your laptop gets stolen, the email that's on your computer, people send you messages, and when they send you a message, the expectation is that message is being delivered to you. They don't, most people, when they write in the to subject, they don't CC, they don't have in their mind, okay, I'm CCing Google, all of their employees, I'm CCing a couple of hackers, I'm CCing many NSA employees, and possibly other governments are also going to be CC'd on this email, so I should be, keeping all that in mind. Most people just think that I'm talking to this one person, and this message is intended only for them. But if your email isn't secured, if the person you're sending it to doesn't secure their email, if the channel over which the email is being sent isn't secured, that email is very close to public dialogue. But that's not how it's presented. Many people still view email as an electronic form of snail mail, when in fact it's actually much more public than snail mail. So that ethical conundrum is what brought me into InfoSec. And after working on the problem of securing data at rest through a commercial product, I started working on securing data in motion as it's going over the wire. And that's a much more difficult problem. Because whenever you're dealing with securing data in motion, you have to deal with all kinds of possible attacks, the most fundamental of which is what's called a man-in-the-middle attack. So I'm going to ask the audience, you guys, a few questions, because I want to know how much you know about these problems. I want to know what your, what your knowledge set is, so that it can help me guide the conversation. First of all, and please everybody, answer honestly, it will just help the whole thing go along better. Show of hands, who here knows what a man-in-the-middle attack is? Okay, I would say about 80 to 90% of you know what a man-in-the-middle attack is. And I'll briefly cover it then, just really briefly. Show of hands, who here knows how HTTPS works?
Vaguely or in specific?
Okay, so about 5 hands were raised. I'm surprised. I was expecting more hands to go up. So, show of hands, who here knows what TLS is?
Stuff underneath HTTP.
Okay, about 7 to 8 hands went up, which doesn't make sense. Because if you know what TLS is, you should know what HTTPS is. Show of hands, who here knows what TLS, the acronym, stands for? About the same number of hands went up, so at least you're being slightly consistent. Okay, good. Show of hands, who here knows what X509 is? About 2.5 hands went up. 3 maybe. That's good. Unless some of you know and aren't raising your hands, which is annoying. Okay, now these questions were stacked in this order because I want to make a point here. That to really know what HTTPS is, you have to know what all of those things I just mentioned are. If you don't know what all those things I just mentioned are, you don't know what HTTPS is and you don't know how it works. And it looks like most people here don't know how HTTPS works, so that's where I'm going to start, is describing how HTTPS works. Now, I was called here somewhat last minute, so I did not prepare any slides. I have some slides that I use for, for other presentations and whatnot, but using a whiteboard is often just as good, if not better. Okay, so here we have Alice, and she wants to connect to Facebook.com over HTTPS. Now, this is actually, in its simplest form, to establish a secure communications channel. Every single secure communications protocol needs to do essentially the same thing. Uses what's called asymmetric encryption. Show of hands, who knows what asymmetric encryption is? Okay, about half the people raise their hands. Asymmetric encryption is contrasted against symmetric encryption. And actually, I would like to keep track of time. 10:30, okay. Asymmetric encryption is contrasted against symmetric encryption. Symmetric encryption is very simple. It's when you know a password, and you use that password to encrypt some data. That's what symmetric encryption is. There's a password. Sometimes it's referred to as a shared secret. It can be shared or not. Asymmetric encryption is slightly different. In asymmetric encryption, there are 2 bits of information. One of them is secret, known ideally to only one individual, one organization. It's supposed to be treated as a secret. And another piece of information is intentionally treated as public information. These two bits of information are referred to as a public and private key pair. The nice property of public-private key pairs, this is how asymmetric encryption works, is the following. So if you encrypt with a private key pair some message, you're going to get ciphertext. However you spell it, with an I or an Y. If you do this operation, encrypt with the public key, and then encrypt encrypt, and you pass to that the encrypted message, you will get back the message. This is the basic idea of public-private, of asymmetric encryption, is that you have these functions, and you can actually switch these around. So you don't have to, this could be the public key, this could be the private, and this could be the public key. It doesn't really matter. These are just two keys. And either way, it has this property that if you have a message, and you encrypt one with the private or public key, and then you encrypt that, again, with its corresponding key, you get back the message again.
It's really bright.
Why is this done?
Okay.
The reason this is done is so that if you want to be able to communicate with me securely, I give you my public key. No worries.
When I get a code.
And then what you do is you take the message that you want only me to read, and you encrypt that message with my public key. The public key is public information. Anybody knows it. And then only I will be able to decrypt that message because I have the corresponding private key. So exactly like this. You want to send me a message, say hello to me. I tell you what my public key is. You do this operation, you encrypt it. Now nobody on the planet, supposedly, except for me, because I have the corresponding private key, can read what the actual message was. That's the basic concept of asymmetric encryption. Any questions at all about that? And if you don't ask a question, I'm assuming you understood everything I just said. No question.
Every bit of it.
Every bit of it. You have a question about every bit of it?
No.
You understand every bit of it?
But just to be clear, does this kind of idempotence thing there, where it's going, just passing the encrypted, does that apply regardless of the underlying scheme, or is this only for the the prime base, large integer sort of encryption things? Is there some other Is there something that makes that work?
Prime numbers, yeah. Usually
I know, but it doesn't have to be, for example, does your encryption scheme have to be based on prime numbers, or can it be based on another sort of scheme? I'm just curious. This is kind of off topic.
The question is, does the underlying math here have to be based off of prime numbers, or can it be based off of something else? The answer is, I don't know, because I'm not a cryptographer. I have only heard of these schemes that work with prime numbers.
That's off topic.
Maybe somebody knows if somebody knows the answer to that question, if there is another way to do this without prime numbers.
Well, I think the basic idea is independent of the underlying.
Yeah, the basic idea is independent of how you actually do this, but I was just curious if anybody knew. Okay.
Elliptic, for example, is not prime. It's a different idea.
What was that?
Elliptic key cryptography.
Elliptic key cryptography. That's, okay, that's a good point, yeah. Elliptic key cryptography. Right. Okay, so actually, yeah, it doesn't have to be prime. I just realized.
The question is, does this thing work here for elliptic curve cryptography as well? Is there similar?
Yeah. This is the basic concept of asymmetric encryption.
Okay.
Now, I'm not exactly sure if they're completely interchangeable or if you have to apply them in a certain order, but I think they are interchangeable, but that's a technical detail, that doesn't matter. But this is also actually how Bitcoin works with, when somebody has an address. What is the address? When you want to send somebody money in Bitcoin, what are you sending that to? What you're doing is, the address is simply somebody's public key has been passed through a hash function. So they take a large bit of information, and they pass it through a function that turns it into a number of a fixed size called the hash. And that's what you're sending coins to. So, back to HTTPS. The problem that we want to avoid in general, so say that this was just HTTP and you went to httpfacebook.com, what could happen? Well, anybody in the middle here And most of you raised your hands, I think, and said you knew what a man-in-the-middle attack was. The problem is that somebody in between you on your way, on a router or something like that, can spy on your information, can see it, can also tamper with it, can redirect you to not Facebook.com and make you think it is Facebook.com. They basically have complete and total control of the communication at that point. And that's what HTTPS was designed to try and prevent. Now, it doesn't prevent that, but it tries. But using blockchain technology, you'll see that we can actually stop the man-in-the-middle attack. For all except the fundamentals, which is like, if the private key is exposed, or there's a problem with the cryptography, or there's a bug in the implementation like Heartbleed. Those are the fundamentals that affect all secure communication systems. But in addition to those fundamental ways of having a man-in-the-middle attack, today's system allows many other ways of doing a man-in-the-middle attack, and that's what I'm here to talk to you about. So how does today's system work? Facebook and any secure communication system, again, this problem applies to any secure communication system. Anytime you see like a secure chat app out there, and people claiming that it's secure, they're probably wrong. They're probably skimping on the details a little bit. Even Apple, in its copy, in its marketing copy, says that they cannot be coerced by the government to spy on you. That's not actually true. They can be coerced by the government to spy on you by doing the attack that I'm about to describe. So Facebook has to get their public key to you. If they can't get their public key to you, what happens? Well, let's say that there is, an evil man in the middle. Or maybe benign, somebody who thinks they're benign, but that's what they think. So what they're going to do is, as Facebook sends their public key, they're going to just swap it out for theirs. So they're going to communicate with Facebook as though you were communicating with Facebook. And in the meantime, they're going to give you their public key. So this is the key for Facebook. And this is the key for the man in the middle. And once that little swish happens, that's it. That's game over. They are able to decrypt everything that you sent to Facebook because they sent you their public key. You're thinking that you're talking to Facebook, but you're talking to the man in the middle. They then take the decrypted information that you are sending to Facebook, and that Facebook is sending to them. So if we're going in this direction, they simply re-encrypt the information with Facebook's key, etc. And that's the basics of a man-in-the-middle attack. So how does HTTPS attempt to prevent this? That's where the term X509 comes in. So when your web browser tells you that, it throws up a lock icon and tells you that the communication to this website is secure, what is it actually saying? It's not actually saying that the communication with this website is secure. What it's actually saying is there is a system called X509. And X509 is what's known as a public key infrastructure, PKI. Just in case if you want to know that. And what that means is it is an infrastructure that's designed to distribute public keys. And in this case, it's used for trying to assert that the public key that you receive from Facebook actually really came from Facebook. But the truth is that the way that they designed the system is they said we're going to have authority figures who are responsible for making these assertions. And they're called certificate authorities. And there are a whole bunch of certificate authorities. There are different numbers floating around. I think that the EFF or somebody else or somebody associated with the EF did a count. And what they did was they looked at all the various different operating systems out there, all the various different web browsers out there. These things come shipped when you get an operating system or a web browser. They come shipped with a list of public keys that belong to these certificate authorities. And when you aggregate all those together, I think they came up with a number that was over 1,000 certificate authorities. On any one computer, there might be a few hundred. But in aggregate, the world, collectively trusts the least trustworthy. This is a very important point. There's over 1,000 of these certificate authorities, and when you connect to Facebook.com, you are not trusting the group, you're trusting the bad apple in the group. That's who you're trusting. And you're not even trusting the bad apple in the group, you're actually trusting potentially somebody outside the group who can either coerce or hack either the bad apple or the most incompetent of the certificate authorities, whoever. So you're actually trusting way, way more than 1,000 entities whenever you connect to any HTTPS website.
So every single one is a single point of failure.
Yeah, every single one is a central point of failure for the entire internet. Why? Because every single one of these certificate authorities has the power to create, to sign certificates on behalf of websites. And it's a great business because it costs them $0 to do this, and you pay them a yearly fee for most of them. There's about 2 certificate authorities, to my knowledge, maybe 2.5, 3, something along those lines, that actually will give you a certificate that web browsers respect for free. One of them is called Start SSL. The other one is a project that I think is a collaboration between the EFF and Mozilla, which just started recently, called Let's Encrypt. And the reason why I'm telling you that is because don't be a fool. Don't pay for insecurity. The companies out there who are paying for hundreds of dollars a year for these fancy green bar, there are some certificates called extended evaluation certificates or validation. They cost more than other kinds of certificates because they make the color of the address bar change.
What's the web? Who gives you the free one? Can I
Start SSL. It's one word. Start SSL. So one is Start SSL. They're a little bit more difficult to use than Let's Encrypt. But you can use
wildcard?
They don't do wildcard. What they do is they give you one domain and one subdomain. And usually the subdomain is because most people have www as a subdomain. And Let's Encrypt, I don't remember what the deal with them is. But it's effectively a wildcard because you can just keep asking for they don't have a limit, really. I think they do. Like they might have like a script. If you start like getting a whole bunch of them, they might stop. But other than that, you can ask pretty much for as many as you want, as long as you're being reasonable by their terms. So companies that pay, companies like PayPal, all the banks out there are paying, and other websites pay hundreds of dollars for these fancy certificates that make the address bar green. They're wasting their money because most consumers, most web users are not going to notice whether or not when they go to a website the address bar is green or not. That's not even something that they even really understand is a meaningful thing. They just want to know if when they go to PayPal.com, if they're able to see it without any kind of warnings. That's number one. Then for probably a small fraction of those people, they care if there's like a little lock icon, if they can see that lock icon. And then for a tiny, tiny, tiny fraction of those, they even know that the thing is supposed to be green, a different color or something like that. So anybody can, or not anybody, but a lot of, somebody can obtain a fraudulent certificate from one of these authorities, either by hacking them, by coercing them, etc., and then use that to man-in-the-middle financial websites or anything else. And most people are not going to notice that happening. It's very, very difficult to detect these attacks. And yes, they do happen. Question?
So all of these CAs are supposed to have a key in the browser, right? So browsers only have so many, if you look at it, they've got like a bunch of keys in there that are from CAs they trust, I think.
Yes.
Is that correct?
Yes.
So if you have like whatever Start SSL just wants to be created by the EFF, how are they going to get their keys into browsers?
Okay. So the question is, well, comment then a question. Comment is, so web browsers ship with a list of certificate authorities, the public keys to them that they trust. So if you want to create a new certificate authority, how do you get your certificate authority's public key into one of these lists? There's probably a process for doing that in place. I'm fairly certain there is a process in place for doing that. And the answer is that it's not easy to get your certificate authority's key into a web browser. And that's one of the reasons why there are so few certificate authorities that are trusted by web browsers that offer free certificates. EFF was able to get this Let's Encrypt thing going because they had a collaboration with Mozilla, and Mozilla happens to have their own web browser, and Mozilla collaborates with Google, who also has their own web browser, etc. Yes, back there.
So actually the situation is sort of much worse than you're describing. It's almost routinely people are being man in the middle because a lot of businesses, want DDoS protection. So they often will, work with either a CDN.
Are you talking about Cloudflare?
Yeah, or yes, I mean, any a CDN or any DDoS protector will actually be a man in the middle. That's the only way they can do the job. Yeah. And so people are being routinely man in the middle in the name of like.
In the name of security, man in the middle in the name of security.
That's also how like all the firewalls and APs that do traffic filtering are doing it now too.
I didn't quite catch how this.
Okay, all right. So I'll comment. So the comment was that he said that the problem was actually worse than I'm describing it, which it's hard to imagine how it can be worse. But yes, he's right. It's worse than I'm describing it because it's now become very fashionable because these things are because getting a free certificate is not easy. There are companies like Cloudflare who provide DDoS protection, distributed denial of service, against websites. So they provide protection from that attack. And lately they've been offering free HTTPS to their customers. And how are they doing that? They're not doing it the way that Start SSL and Let's Encrypt are doing it. They don't have a certificate authority in web browsers that's accepted by that's accepted by web browsers. What they do is they use a technical thing called subject alt name to they buy their own certificates essentially, and they tack other people's websites onto these certificates. And because their certificates are legitimate, when they add other domain names to that list of certificate, those kind of gain the legitimacy that they're already, they kind of grandfather them into their certificate, is what they do. And it is a man-in-the-middle attack that people either knowingly choose to participate in or unknowingly choose to participate in. I suspect that for most people, for most businesses that go with Cloudflare, it's mostly unknowing. Like they think they're securing their visitors' connections, but what they're doing actually in reality is Cloudflare is becoming this huge central point of potential failure and also potential point of surveillance, where, especially, and it becomes, the more customers that Cloudflare gets, the more of an incentive there is for a government to come to Cloudflare and say, listen guys, you know that little step you do where you decrypt and re-encrypt traffic? Just please add a little copy of all of that information and send it over to us. And don't tell anyone else you're doing that because we just sent you a national security letter. And then people think that they are, again, they have that little lock icon and they think they're being secured, but in reality, that's not at all what's happening.
Yeah, it's not to make Cloudflare out to be a bad guy because what I'm saying is that, before them, you had CDNs and some of the CDNs tried to offer you SSL with the CDN. The only way they do that is by doing what we described Cloudflare is doing. Right.
So yeah, Cloudflare isn't the only one.
And similarly for people who were saying they were providing DDoS protection with SSL, this is what they needed to do.
Yeah, so CDNs, content delivery networks, often use the same trick, or technique, not trick. Content delivery networks, they specialize in making copies of your content and putting them on servers around the world so that your content gets to people really quickly. And so they have to, because they have to decrypt and re-encrypt traffic, otherwise people won't be able to understand the garbled mess for your JavaScript or your CSS, etc. So these kinds of attacks are happening routinely, sort of knowingly and unknowingly, just because of how encryption works. And then they're also happening like as legitimate attacks. And the problem with this is that it's incredibly difficult to detect one of these attacks. To give you an idea of just how difficult it is to detect one of these attacks, there are only a handful of companies on the entire planet that are, first of all, capable of detecting one of these attacks. Really, because and those are the companies that make web browsers. Because they're in this special privileged position where they can modify their web browser however they want. And so, for example, one of the most notorious attacks, like probably the most notorious attack to date that happened, was the DigiCert attack of, I don't remember, it might have been 2008 or something like that. And the reason that attack was detected was because Google is aware of these attacks. So what they do is they say, for our websites, for Google, we're going to take our certificate authority, we have our own, and we're going to pin. That means we're going to take our public key and we're just going to put it into every copy of Google Chrome that we distribute. And since the web browser now knows what the public key should be, they can detect if the public key is switched on them. But notice a few things. This is Google protecting their own websites. They cannot use this technique to protect other people's websites. This is Google. So that's one of a handful of companies. The other companies that can use this technique are Apple, because they have Safari, Microsoft, because they have Internet Explorer, Mozilla, because they have Firefox, and for the small fraction of people who use Opera, there's also Opera. And that's it. And in spite of that, it took Google about 2 months before they detected an attack that was happening on their users as they were connecting to Gmail from, like, I think it was Iran or something like that. So 2 months. In spite of being one of the few organizations that's capable of detecting these attacks, it took 2 months to actually detect it. And when they detected it, they discovered that this attack was being done actually not just on Gmail and not just on Google websites, but on U.S. federal government websites, like the CIA.gov, FBI.gov, and I think hundreds or thousands of other websites. And it was a huge scandal and all that. But these attacks probably happen routinely, and they're incredibly difficult to detect because the system calls the attacks legitimate. As long as you have a certificate that's been signed by one of these certificate authorities, the system doesn't actually view it as an attack. It considers it to be a legitimate secure connection. And when you have a system that cannot differentiate between legitimate secure connections and man-in-the-middle attacks, you have a big problem. Yeah. So,
I'm sorry to jump ahead a little bit, just so that I get the picture here. I think what you're going to suggest is that you can use essentially the public keys on a blockchain to replace the CAs. I'm sorry I'm jumping ahead, but I'm just trying to get a picture of how this is tying in. Is that correct?
That is correct, but my plan is actually to annoy you guys with problems before I get to the blockchain.
Okay, I mean, okay, so I'm just trying to see how it's fitting in. Thank you.
Okay, so moving on to the next problem. So this is HTTPS. This is the mess that we find ourselves in with HTTPS, with these certificate authorities. The basic idea is that we're trusting people who should not be trusted. That's a bad idea, and that's why we have this problem. What's another problem that we have related to public key infrastructure? Another problem that we have is GPG. Why is GPG a problem? GPG is a problem because it's one of the few methods right now that people have for sending secure email to each other, or secure messages to each other. But it's for the technical elite only. Regular users need not apply. And in spite of lots of great projects out there trying to make this stuff easier, you cannot make GPG usable if the user ever hears the word public key. So it's just not going to happen. So when GPG becomes usable is when users never have to worry about public keys. How does GPG work? GPG has, again, a similar problem, which is how do you get somebody's public key to send them an encrypted message? Currently, there are what are called GPG key servers out there, and you search the key servers for an email address, and they're supposed to return to you the public key for that person. There's multiple problems with this. First off, oftentimes when you search for an email address, you get multiple results. So how do you know which one of those public keys is the right one? Another problem is that the connection to, oftentimes, might not always be the case, the connection to these GPG key servers is sometimes just in HTTP. So a man-in-the-middle attack can be done to swap out the keys as you're requesting them. Sometimes it might be over HTTPS, but then you still got this other man-in-the-middle attack I just described happening. Then there's another problem, which is, well, and this happens all the time, by the way, like happens to me and my friends. Your computer dies, you lose your private key, and you have to generate a new one. So now, any secure messages that you get, first of all, you cannot read anymore. And second of all, you have the problem of convincing people. Sometimes you can't even meet them face to face. Sometimes you're communicating with people on the other side of the world. So now you have to convince them, oh, no, that's not my public key anymore. Use this one. Now that you're putting the other person in the position of figuring out whether or not you're lying to them and trying to attack them by telling them, some sort of a fake public key. And not just that, but then they have to actually go through the rigmarole of getting your new public key and updating their software with the new public key so that they can now send you encrypted messages again using the new one. So GPG is a usability nightmare because of that, and it will never become, there will never be a GPG for the masses as long as users have to deal with these private keys. Oh, there's one other problem I forgot. There's this concept of revocation also. And the concept of revocation exists both as a problem in HTTPS and GPG. Revocation is what you're supposed to do. It's a thing that nobody does, but you're supposed to do when your private key is compromised, or you lose it or something like that. So when you lose a private key, or your private key is compromised, you're supposed to make a statement in these systems that says, my private key was compromised, or whatever. Don't use that public key anymore out there, it's illegitimate. And you're supposed to send this statement over to some entity, some authority, that then is supposed to tell other people about it. Nobody does this. Nobody does this. By nobody, I mean like for really small values of, small values of 1. Because sometimes in GPG you have to create these like revocation things in advance. And if you haven't created a revocation thing in advance before you lost the thing, you can't create it in the first place. And then it's just confusing how to do this. Most system administrators don't realize this. They just update the public key and the private key that they have and use that. And that's a nightmare, by the way. That is a really insidious attack. That's the worst man-in-the-middle attack that can happen to you. And I think it happened to me. I'll describe how this works. So if you remember, a while ago, there was this huge kerfuffle called Heartbleed. What was Heartbleed? Heartbleed was just a software bug in OpenSSL. OpenSSL is like the software that secures the entire internet. It's what powers TLS. And TLS, by the way, for those who don't know, is the underlying protocol that adds the S to HTTPS. So I was connecting to NPM, Node Package Manager. And I have this web browser extension installed that you guys might want to install, but I really can't recommend it too much because it's a nightmare in terms of usability, and it illustrates again other problems with the system. Certificate Patrol is a Firefox-only browser extension that will tell you anytime a certificate changes. It will give you all the information about what changed, and it will tell you whether you want to accept or deny. So I was using NPM. And then one day I noticed that the certificate changed. I don't always do this, but whenever I see that, sometimes I reach out to the people who run the website. And I ask them, is the fingerprint that I'm seeing legitimate? So I did this on Twitter, and this was after Heartbleed. And this was because everybody at that point in time was changing their certificates because of Heartbleed. It was a nightmare for me to browse the internet because every website I visited, I'd get this thing. Firefox would slow down. I'd get this giant sheet that would tell me that the certificate changed. So I reached out to Node Package Manager, to NPM, and asked them, you know, did this change? Is this your correct public key fingerprint? And they said, yeah, that's the correct one. And for probably 99.999 repeating % of the people on the planet, you know, that would have been the end of the story. But I thought about it a little bit, and I asked, okay, wait a second. When did you make this change? And they were like, oh, about 2 weeks ago. And then some alarm bells went off in my head. Because I had been visiting NPM, the Node Package Manager website, fairly regularly during this time. And I'm pretty sure I visited it just yesterday, the day before that happened. And I'm pretty sure, well, yesterday I didn't see any kind of certificate change. So if they changed the certificate 2 weeks ago, why was I only just now seeing the change, in other words? So that's an example of what could have been potentially a man-in-the-middle attack on me or other people. Because of Heartbleed, you could extract the private key from any website that had HTTPS. That allowed you to man-in-the-middle connections, and it allowed you to man-in-the-middle connections using a legitimate certificate. One that the website actually created. Not one that was obtained from some other certificate authority, but the actual legitimate one. And then there's this, you know, so there's this man in the middle that's in the way, and you're seeing the legitimate certificate that was obtained thanks to a bug. And only until the man in the middle leaves will you actually see the legitimate one. So that's a particularly insidious form of a man-in-the-middle attack. And again, these kinds of things just are not detected. They're very difficult.
So are you sure that that's what happened, or is there some other explanation?
So yeah, we had a back and forth on Twitter to see if there was some other explanation. Some theory was that, well, maybe the old key was cached or something like that. But I doubt that it was cached for 2 weeks. I don't think that it's supposed to be, you know, cached for that long of a period of time on a CDN when it's changed. And I also don't understand how it even could be cached, because if they change the public key that they're using, I mean, the CDNs would need to, yeah, so it's, yeah. I don't know, but it's dangerous. It's dangerous for multiple reasons, and especially dangerous in the example that I just gave, because what is NPM? Node Package Manager is a centralized repository of software that all of you guys are using, most of you people are using, to install software on your computer. And then, so you're getting software from the central repo that could be man in the middle to install backdoors on software. You're putting that in your projects, and then you're distributing your software to other people. So you could even have a security audit on your code, and they could say, yeah, everything's totally legitimate. But you make a release all of a sudden, you know, the NSA or somebody just like swaps out the code, you know, in real time, adds a little thing into there, a go-to fail or something like that, one extra one, and boom, that's it. Suddenly, a project that's being used by hundreds of millions of people has a backdoor in it. Huge problem. I told you I would annoy you with problems, so I'm going to annoy you with another one. Here's another problem. This one comes from the area of privacy. So far we've been talking about security. Now I'm going to move into the realm of privacy, and I told you that that would be a theme of this talk. The difference between privacy and security is privacy is when I care whether or not people know what I'm doing, and security is when I care about the integrity of data, and that it's not knowable. So security, you can have a secure connection to a website, but the fact that you visited that website might be public information. If I care about the fact that I visited a website, then I care about privacy. If I care that my communications were concealed or just unreadable, that's security. So there's this thing called the Facebook login button. Now Facebook is on a mission kind of like the Mongols back in the day to take over the world and get everybody onto their platform. And this is concerning. It's not good ethically for a centralized entity to have everybody using their platform from a privacy perspective. No matter how much Facebook tries to mitigate privacy concerns, they will never be able to completely address people's privacy concerns by the very fact that they're centralized. So even if you're not on Facebook, you're affected by Facebook because people will tag you in photos. They are able to use other social media websites to develop what are called shadow profiles about you, which, to my understanding, are profiles. The way that I heard it described is it's kind of like a mental model of who you are and what your likes and dislikes are. And you don't necessarily have to use Facebook. And sometimes Facebook will actually make just an all-out public profile of you without you being on the website or consenting to it. And there's they just ignore your complaints. But what's really annoying is these login buttons. And people don't realize how annoying these login buttons are. Because every single website that has a login button or a like button or any other kind of a Facebook widget on their website, that is a signal to Facebook that you visited that website. And they can then track you across all the websites that you visit throughout your day. And why do they do this? Because they want to be able to target you with advertisements and sell you things. They want to know what you like so that they can tell other people what you like so that they can sell you things. Unfortunately, as annoying as spam is, what's worse about this is that the government can go, and they do go, as we learned from the Snowden links, and say, hey, Facebook, we want to know, all the information about these groups of users and where they've been going and what they've been doing. And by the way, don't tell anyone that we asked you that. National security letter. So that's why this Facebook login button is really annoying. And the good news is that you can actually, this is fairly easily preventable. If you want to prevent this, install Ghostery, the browser extension, or Disconnect. Those are two browser extensions whose sole purpose is to prevent websites from tracking you as you browse the internet. And they will block these Facebook like buttons and login buttons and all that other stuff. And you can also selectively unblock websites, if for some reason you want to use them.
Are these plugins themselves not a security hole? Because that code can be updated, your plugin can be updated, and then you've got a different kind of attack.
So the question is, are these plugins themselves a security hole because they can have a backdoor or installed into them or something along those lines? The answer is, while they are not necessarily a security hole, they are potentially a security hole. Any piece of software that you run on your computer can potentially have malware installed on it. And the blockchain is actually something that can prevent a lot of these problems, including that one. So we'll get to that. But first I want to know your problem. Okay. So let's see how we're doing for time. It's 11:12. I'm going to take let's take a short, 5-minute break. You guys can, first, if there are any questions, let me know. Any questions up to this point? Yes?
When you see that like button on the page, do you have to interact with that for it to track you?
No. No, you visited that website. You made a request to Facebook.com. Facebook knows you made that request. And because of cookies, when you're logged into Facebook, those cookies are sent along with that request. So Facebook, if you're logged into Facebook, if you go to Facebook.com and you don't see a login page, you just see your messages in your profile, then it's even worse because not only do they know your IP address, but they literally know that you visited that website.
This isn't any better with Google or Yahoo. I mean,
No.
AdSense and all these guys are tracking retargeting is how advertising on the web works these days, right?
Yeah, so the question is, it's not why am I picking on Facebook, essentially? Is it any better with any other website? No, I know. This is a problem with Google+, this is a problem with Twitter, this is a problem with all of these websites who are doing these little login things. And we're going to talk about a solution to that after the break. Yes?
If you're not logged in, is it just the IP address that goes, or is it the browser identity string as well?
The browser identity string as well, yeah.
Oh, so they can do the fingerprinting?
They can do the fingerprinting, yeah. Because every time you make an HTTP request, your web browser sends along with that HTTP request the user agent string as a header and some other stuff. So it's not just your IP address. And EFF has a wonderful tool that you can use to see how identifiable are you just from the headers that your browser sends. And for most people, you're extremely identifiable. Especially in this room. You guys are all very identifiable. You guys are all weirdos using Linux and latest version of Firefox and Chrome beta versions. Easily identifiable. Okay, no more questions. Let's take a short break. Let's take 5. Deal with all this mess.
Solutions.
Now, to bring us on the path towards solutions, I need to introduce one more system called DNS. Show of hands again. Who here knows what DNS is and what those 3 letters stand for? Okay, about 60% of you raise your hands. DNS stands for Domain Name System. And what is it? All it is it's a key value mapping, or just, a mapping from names to IP addresses. I probably shouldn't ask this question because you probably all, well, I'm not going to bias the answer. Who here knows what IP addresses are? Raise your hands. Okay, just about everybody raise their hands, and the people who didn't probably know.
The question is, at what level, do you want? Always fuzzy, like. I'm not
Okay,
sure what level do you want to know what IP address is?
Well, okay, so IP addresses, like many computer people know, are how you find computers online. They are the primary means with which you find a computer through a network. And the reason why we have DNS is because few people are capable of memorizing numbers, just arbitrary numbers for whatever websites. And also, numbers are not very conducive to brands. Numbers are usually associated with prisoners, not brands. So if you want, like to have a nice brand online, you probably don't want it to be a number. You probably want your people to rally around a name. And that also helps people find you, because names are far more memorable than numbers. For humans, for whatever reason, we're not calculators for some reason. So when Alice tries to go to Facebook.com, the first thing she probably does is she either clicks on a link to Facebook.com or she actually types Facebook.com into her web browser. And then it's up to DNS to find out what the IP address is of Facebook.com. Now, DNS is a hierarchical system. There are a bunch of TLDs at the top. And TLDs stand for top-level domains. These are things like .com, .org, et cetera, et cetera, et cetera. And at the very top of the internet, there are a dozen servers or so that manage these top-level domains. And they know they have a registry to other name servers that are responsible for things like Facebook.com. I don't know why I keep using Facebook.com. It's just, well, just continuing the story. So, it just shows Zuckerberg is really good with his marketing. So, Alice asks for Facebook.com. Some name server here sends over an IP address. A DNS server sends over an IP address. And again, you have the man-in-the-middle attack. What happens if, when you ask for Facebook.com, you're given the IP address of some other malicious server that looks like Facebook.com, or for a bank that looks like Facebook.com? Long story short, because I want to bring us to solutions more quickly, DNS is actually not a big deal. It's not a big deal if the DNS server lies to you about what Facebook.com's IP address is. It's only a big deal when you're dealing in two situations. When you're connecting to a website over HTTP, or if an attack called SSL stripping is being used on you. Let me briefly describe how that attack works. So, Facebook.com now, thankfully, uses HTTPS by default. A few years ago, they didn't. They used HTTP, and then a DNS man-in-the-middle attack could be fatal, because users have no way of distinguishing between a legitimate server and a non-legitimate server. Then they added HTTPS. Unfortunately, there's an attack called SSL stripping, which is where a man in the middle establishes an HTTPS connection this way to Facebook.com, and then gives to you an HTTP connection to Facebook.com. So they're able to read everything in plain text, and so is everybody else in the cafe. And then they just re-encrypt it, you know, as though they were you to Facebook.com. They pretend to be you. And the user experience, the user point of view, what the user sees is they see Facebook.com in the web browser without a lock. Unfortunately, most users aren't going to notice this. So they invented a thing called HSTS, which is something or other, something state, I don't remember what it stands for. It doesn't, which is basically Facebook.com, when you visit it once, says, for the next year, web browser, I only allow you to access me over HTTPS. Never, ever can you ever access me over HTTP for about a year or so, whatever they set the timeout for. And that actually does help a whole lot prevent SSL stripping attacks. Because when a user just once visits Facebook over HTTPS, then from that point on, for the duration of that little timeout, they cannot visit it over HTTP again in that particular web browser. It has to be done for each web browser that they use. Okay, so why is DNS man in the middle not a problem when HTTPS is actually being used? The reason is because if somebody gives you the IP address of not Facebook servers when you ask for it over DNS, let's say they just redirect you to their server, they still have to convince your web browser that your web browser has received a legitimate Facebook.com certificate. And that falls back on that whole certificate authority system that I described before the break. If they can't achieve that feat, then they cannot man in the middle you, even though they've managed to get you to their server. Now, there's still a privacy concern. So that's, notice that, so as far as security goes, DNS by itself isn't really a problem. And solutions like DNSSEC are actually not solutions that we need, and they actually cause more problems than they solve. But it is a concern in terms, in some sense, in terms of privacy. Because the fact that you visited Facebook.com, that piece of metadata is sent in the clear with DNS. So there's this project called DNSCrypt. What is DNSCrypt about? It simply creates an encrypted connection to the DNS server you're talking to, so that when you say, what is Facebook.com, that question is encrypted. Over that encrypted connection, you are given the IP address. And here again, we run into another problem with privacy. Because when DNSCrypt gives you the IP address to Facebook.com, you then have to use that IP address to connect to Facebook.com. And the fact that you're using Facebook's IP is still publicly known information. And if you're concerned about that, you have to use something like a proxy, like Tor or a VPN, to conceal that, the fact that you visited that website. But from a security standpoint, there's not much of a problem with DNS as long as you can do HTTPS. And when you do HTTPS, you have that little concern of TLS man-in-the-middle attacks. So let's move on to the solution. How can we solve this problem? In 2011, Aaron Schwartz wrote a blog post called Squaring Zuko's Triangle, where he described how the blockchain can be used to solve a host of problems, including many of the ones that I just described today. He was one of the first to realize that the blockchain can be used to create a system that had been previously thought to be impossible. This assertion that I'm about to describe is called Zuko's Triangle, named after Zuko Wilcox. It asserts that in any naming system, in any global naming system, you can have only two of three properties. You can either ask for security and decentralization, but then you're not going to get human readable. You're not going to have human readable names. If you've ever wondered why Tor secret services have these weird name things that look like Bitcoin addresses, that's because they're dealing with Zuko's triangle. And they went for security and decentralization, but they couldn't get human readable. Well, with the blockchain, which is fundamentally just a secure, decentralized database, distributed also around the planet, Aaron Schwartz pointed out that you can actually have all three of these properties in a global naming system, which is what DNS is. It's a global naming system. A global naming system that has human-readable names, a little bit of decentralization, not too much, and no security whatsoever. Because the blockchain is this ledger that is only appendable, you can only write to it. It allows you, it can be used, and because it's protected by proof of work, it can be used to make assertive statements like, I registered Mozilla, no, okay, let's do Mozilla.bit. About 3 months after Aaron Schwartz posted that blog post, squaring Zuko's triangle, the first fork of Bitcoin was announced that came and did this, called Namecoin. And it allowed you to register domains on a blockchain using Namecoins. And the canonical TLD that they used was called .bit. So you could register .bit domain names on Namecoin. And this was really cool because it marked another first, in some sense, in internet history. This concept of real ownership. Up until Namecoin, we did not have real ownership on the internet. Maybe there were some other systems, but Namecoin really ingrained this concept of real ownership. Actually, Bitcoin gave you real ownership of your money. And before then, people had to rely on third parties, not themselves. So you could not, with Bitcoin, prior to Bitcoin, you had to rely and trust on PayPal, on the entire banking infrastructure, etc., to not mess with you, and to keep your funds, secure, and not take them away from you. Suddenly, Bitcoin came onto the scene, and it was possible, all of a sudden, for you to be in charge and to actually own digital currency without having to trust anybody else. Before, the closest you could get to that was to either take out some cash, put it under a mattress, or to some bars of gold. Now with Bitcoin, it became possible to do the digital equivalent of that. And then with Namecoin, it became possible to do the digital equivalent of having a name, actually owning a name online, that no matter where you went in the world, when you looked up that name, you would get the same piece of information as somebody else on the other side of the world. And that's what the internet effectively is with websites. These are names that are supposed to resolve to the same thing no matter where you are in the world. So real ownership, however, comes at a cost. It's a double-edged sword. Because with real ownership comes the possibility of real loss. Just like when you have a car that you own, somebody can go break into your car and now it's theirs. And you have to go somehow get it back. Whereas with today's online system, because you're trusting somebody else to maintain the security of your digital assets, your name, for example, most people's identity online these days is oftentimes synonymous with their Twitter handle. And you're trusting Twitter to allow you to speak your mind online, to not, take your account away from you, to not censor you. You're trusting them to be a good steward of your name. And so you're actually borrowing a name from Twitter, just as you rent your website from ICANN, which is the international governing body over DNS and that whole naming system. And there are in the news every now and then pops up a story about how such and such a website had its domain name seized, taken away from them, from the owners. Namecoin stops that. Namecoin stops seizures of domain names. Because the only way to seize a Namecoin domain is to either go to the person's house, get their laptop and steal their private key, or hack into their laptop and steal their private key. Much more difficult than just saying, hey, we're the government, so we can do whatever we want and steal people's stuff. But Namecoin doesn't just solve the problem of domain seizures. The concept of using a blockchain to do a secure, decentralized, distributed key-value database solves so many other problems. It actually solves the man-in-the-middle attack, for one. So if my computer were running a Namecoin node, it would use the sort of trustless infrastructure and the power of proof of work to retrieve all of the blocks that are Namecoin and look up whatever okturtles.bit's IP address is. But you can do more than just looking up what an IP address is. You can look up somebody's public key. Remember I mentioned that X509 was a form of a public key infrastructure? Well, the blockchain can also be used to do public key infrastructure. But it can be done in a way such that you trust the security, you're not relying on an untrustworthy third party for your trust. You're trusting the security of the system itself. Proof of work in the case of Namecoin. And that's several levels above that. So once you have a blockchain that you can look up public keys for names, human readable names, you can do email just like email is done today, but secure. So somebody out there, and I encourage somebody to actually do this. Here's a programming project idea, because I'm not going to do it. I'm just working on the system that makes this possible to do, called DNSChain, which I'll get to next. You can have the following user experience. I want to send an email to greg@okturtles.bit. So I just type in greg@okturtles.bit into my email client, type my message, and send. That's the user experience that people are used to. That's how email is supposed to work. But with the blockchain, you can have the client software automatically retrieve the correct public key at this point in time. The person you're communicating with can update their public key in the blockchain, can recreate their private key, recreate their public private key pair as much as they want, and update the fingerprint that's stored in the blockchain. And so client software will always have the right key, as long as you know what their actual email address is. The same goes for secure text messengers. So Apple, for iMessages, can provide the same user experience that people are currently used to with iMessages. And they can be truthful in their marketing copy and say that they cannot be coerced into spying on their customers. Because right now they can be. Right now the government can go and say, we want you to spy on these people. Anytime they send an iMessage to each other, we know that your iMessages is technically end-to-end encrypted, but because you're acting as the public key infrastructure, and because you're the one who's responsible for distributing public keys, we just want you to substitute the user's public key for ours, please, and then tell us what they're saying. So Apple can be truthful when they say that that scenario cannot happen if they were to switch to using a blockchain-based approach and store users' public keys in a blockchain. The user doesn't ever have to know that this is happening, but they benefit from real end-to-end security. And the same can be done with websites, with HTTPS. Instead of relying on a bad apple out of thousands of bad apples, maybe I shouldn't be that mean, but you know, they can rely on data that almost nobody can mess with. And actually, let me go into that a little bit. There's the 51% attack, right? What can the 51% attack do? Notice that not even the 51% attack can change the information that's in the blockchain. So I can store my public key for my email in the blockchain, and somebody can 51% attack the network, and it doesn't really bother me too much because they cannot change that entry without my private key. All they can do is double spend and censor the network, prevent updates from coming in. So potentially they can wait for my name to expire in the blockchain. In Namecoin, it's about, I think it's a little over half a year, the expiry. Like if you don't do anything, if you don't send a transaction to the blockchain, it'll expire after about half a year in Namecoin. And the rules can be different for different blockchains. And by the way, Namecoin isn't the only one that's doing this. Recently, some of you might have heard of a company called OneName, released a project called Blockstore, which is a key value database that uses the Bitcoin blockchain. What they do is they simply you've got the Bitcoin blockchain going along, and they use a very small piece of small amount of data. What they do is they just take a fingerprint, a hash, and they store it in a transaction in the blockchain. And what these hashes are they are keys into a DHT. I mean, this is often how a DHT is represented. You know, it's sometimes it's a structure that's circular. Sometimes it can be done in other ways. And it's the same kind of technology that powers BitTorrent. And then they can store, you know, arbitrary amount of information. The only concern with this model is that there is an availability attack, like somebody can Sybil attack a DHT and make the data unavailable, and that's about it. But as far as security goes, if you're able to access the data, then you've got the actual data. Yes?
Yeah, I had a question on the block store, the DHTs that you're storing. Do you know where they're storing the DHTs? Because
they're using Cademelia or something like that, is the DHT thing that they're using. It's a DHT client.
So the example that you gave about sending over an email using the blockchain to essentially pull a public key of the person that you're submitting it to, that still means the person that's receiving the email has to manage their private key and store it somewhere, right? And so essentially, be it their laptop or some third party that they trust to store their private key, that leads into another discussion of, well, shit, I'm not someone who's necessarily adept at security of my laptop or at a level where I can protect this private key. So then, right?
Yeah, I get what you're saying. Okay, so that's an excellent question. Thank you for bringing that up. The concern was, well, you're talking about getting rid of users having to manage and deal with public-private key pairs and all of that, but ultimately, there is this private key that they have that they use to decrypt messages and sign messages. Well, doesn't that introduce the problem of what you described earlier a few moments ago, where if they lose the private key, they're kind of screwed, or they have to deal with keys again, and that just makes the whole system unmanageable? That's a great question, and there are solutions to that. So, one solution that I'm